So after we have seen the principles of interference and optical holography, we are going to talk about digital holography, in which instead of using a film, we are using a digital camera. So let's talk about hologram generation, how I create the hologram, how I record the hologram, and reconstruction. So in the generation of the hologram, when I record the 3D scene, it can be done in the classic method by optics. So I'm interfering two mutually coherent laser beams, an object beam and a reference beam, and it can be done by computers. I can simulate this entire process in order to create the interference pattern in the end of the process using a computer simulation in order to create, for example, these holographic optical elements. So this is called computer generated holograms, or CGH. So this is the generation, how I record or create the hologram. The reconstruction, meaning how I visualize or extracting the 3D image, can also be done in the classic method by optics. For example, I can illuminate the hologram by the original reference wave in order to create this 3D image floating in air. It might be behind the hologram plane or after the hologram plane, in front of the hologram plane. And it can be done by computers, which is called digital or electronic hologram, for which I'm using a digital camera instead a photographic film. So these slides actually conclude these 4 elements. You can see here that we have the hologram generation. It can be done by splitting a coherent laser beam into an object beam, a light that interacts with an object, and a light that comes directly from the source, and I can use a film or a camera. And this is when the hologram generation is done by optics. And the reconstruction can actually be done by optics as well. I'm illuminating the hologram, the recorded hologram, by a laser, a coherent laser, which is the original reference wave, in order to create the 3D image of the object floating in air. The reconstruction can be done either by optics or by computers. So if the reconstruction is done by computers, I want to take the 3D image captured by optics or by computers, so-called CGH or computer generated hologram, and I want to reconstruct it plane by plane inside the computer. I want to see an axial slicing of this 3D object in order to create a 3D model of the object. So digital hologram is recorded by a digital camera instead of a film, and the recorded hologram actually captures 4 elements: O absolute square plus R absolute square plus the cross terms. 3 of them are unwanted because I just want this O multiplied by R conjugate, because O captures the complex wavefront of the sample, including the amplitude and the phase. The isolated sample field, O, can be reconstructed in the computer. As soon as I'm isolating this element, I can reconstruct the hologram in 3 dimensions, more or less, and then get the slices till the autofocus effect that I'm going to talk about next. But first, let's see how I can isolate this 4th element, O multiplied by R conjugate. This isolation process depends if we choose to use on-axis or off-axis holography. On-axis means that the 2 beams creating the hologram, the reference and the sample beam, have a 0 angle between them. The off-axis holography means that I have a small angle between the beams, so the 2 beams are not on the same axis, and this is why it is called off-axis holography. So this is a practical off-axis holography system. So we have here a laser, we have here a Mach-Zehnder interferometer, we are splitting the beam and combining the beams again in front of the camera at a small angle. So this is why it is called off-axis holography. So if the hologram is an off-axis hologram, the angle between the reference and the object waves create fringe patterns, cosine fringe patterns all over the scene, even if there is no object. So you can see here in at the background, fringe pattern, a cosine pattern, even if the object is not there. This is the carrier frequency, which is originated from the angle between the object and the reference waves. And this cosine fringe pattern get curved, become unstraight if the beam interacts with the object. As you can see here, this is an example of a hologram of a transparent sphere. So these straight lines, these straight cosine lines interact with the object and then they get curved when passing through the object. This is actually the effect that captures the phase of the object. In order to separate this third term here, O multiplied by R conjugate, we can use the following digital process. So we have already recorded the interference pattern and now we want to isolate this fourth term. How do we do it digitally? We are taking the hologram, which is actually the four terms. We are making in the computer a digital Fourier transform. And because of the Fourier transform properties, each of the multiplication turns into correlation. So we are taking the image here, and after the Fourier transform, because of this carrier frequency, we can actually get that each of the high order +1 and -1, are positioned in different locations in space. And the two first elements are the DC terms because they are positioned in the middle of the Fourier transform plane, in the origin of the Fourier transform plane. And then what I can do next, because I just want O multiplied by R conjugate, I can crop this +1 order, the complex Fourier transform of this +1 order, center it in order to get rid of the carrier frequency, and do an inverse Fourier transform in order to go back into the image plane. And then I'm getting O multiplied by R squared, where usually I can ignore R because it is usually a constant, it is usually a plane wave that didn't interact with the object, and therefore I'm getting a complex wavefront O which contains an amplitude. Absolute O might look like the edges of the bead because the bead is transparent, and the phase of the object, which is the argument or the angle of O, might look like that. The phase usually have unwrapping problem, which actually means that the phase jumps like that. And then I can use a digital unwrapping algorithm in order to correct these jumps and get the 3D image or the optical thickness image of the object. Alternative method for this digital process is using the Hilbert Transform. The Hilbert Transform is a way to do the same Fourier analysis without really doing Fourier analysis. Why this Hilbert Transform works? Let's see first. If we do a Fourier analysis, Fourier transform of the hologram, we are getting these four elements. And if I'm drawing a cross section of these elements, so I'm getting the autocorrelation term, these two first terms in the middle, and the cross correlation terms on the sides. And I'm only interested in the green cross correlation term, which actually means that by spatial filtering I can get rid of the DC term, and then if I will look on the Hilbert Transform definition, the definition of a Fourier transform on Hilbert Transform means that I'm actually negating all the negative frequency domain. Okay? So it actually means that I'm taking the cross correlation -1 and flip it all over here. This is what effectively happens in the Fourier domain if I'm taking a Hilbert transform. Therefore, instead of doing Fourier analysis, all I need to do is taking the original hologram and adding J Hilbert transform of this hologram after getting rid of the DC, because it actually means that I'm taking effectively in the Fourier domain the cross correlation term and adding the -1 for the second cross correlation term in order to get rid of him. And that means that I'm actually getting rid from the negative cross correlation term, and I'm staying with OR conjugate, and then in the image plane I'm multiplying by an exponent of the carrier frequency in order to effectively center it in the Fourier domain. So all of this operation is done in the image plane, and this explanation actually shows you what happens in the Fourier domain. So all that is needed is taking the hologram, adding J Hilbert transform of the hologram, and therefore you are getting OR square, and then you multiply it by exponent of the carrier frequency in order to center it and get OR square without the carrier frequency, which is actually the element that you want to extract in order to get the amplitude and the phase of the object. So we have seen two possible digital processes in order to extract the wanted element. One element out of 4 is all that we need. But in fact, here we acquire more than is needed, because only the object term is really needed for the reconstruction. And because we acquire 4 elements and we need to have them separated in space, located in different locations over the Fourier domain, we need at least twice as much resolution cells from the recording medium. So if we are using a digital camera, we need more pixels than is usually needed for a regular image, because we need to record this high spatial frequency of this carrier frequency cosine. And in order to avoid this redundancy, we can use on-axis holography. So in on-axis holography, there is no angle between the object and the reference wave. Because there is no angle, these 4 elements overlap, and it is quite hard to separate them. They are not located in different positions in the Fourier domain, such as what happens in off-axis holography. How do we get rid of them? One of the methods to get rid of them is to acquire more than 1 hologram per each sample instance. So this is one of the methods that are usually used in order to acquire more than 1 hologram in order to reconstruct only one of the elements. So although these 4 elements overlap in space, if we are acquiring 4 holograms and each of them is phase shifted compared to each other, we can use all 4 of them and digital manipulation in order to get the required element R squared, R conjugate, multiplied by O. So we have I1, which is the regular hologram, And then we have I2, and I2 inside of the reference I'm using waveplate in order to create a phase shift of 90 degrees or pi over 2. In the third hologram I'm creating phase shift of 180 degrees or pi. In the fourth hologram I'm creating phase shift of 270 degrees. And by simple manipulations of these four holograms, taking I1 plus JI2 minus I3 minus JI4 over 4, I'm getting R conjugate multiplied by O. There are other methods to do that by 3 holograms and even by 2 holograms and the reference wave intensity. So let us compare on-axis and off-axis holograms. In off-axis holograms, we are using an angle between the reference and sample beam. It's not always a large angle, because if the angle is too large, it is impossible to acquire it because the carrier frequency will be very high and therefore the camera pixels will be too large in order to capture this high spatial frequency. But actually we are capturing all 4 elements, and these 4 elements are separated in space, and it's actually means that we only need 1 frame. But the disadvantage here that we are losing camera resolution cells because we need more pixels, we need more spatial bandwidth from the camera since we need to acquire these 4 terms. In on-axis holography, on-axis phase shifting holography, because the holograms are phase shifted compared to each other, we need several holograms per sample instance in order to cancel these 4 terms and isolate only one of the terms that we need. But the disadvantage is that the sample might change between acquisition time to another acquisition time, which actually means that dynamic samples might change or move between the acquisition frames, and then we will have errors. There are other possibilities such as digital processing. It is quite hard to do that because we need to bounce again and again between the 2 domains and correct the 2 domains between the Fourier domain and the image domain. So we can eliminate these elements using digital processing, but it doesn't always work fine. So because the desired signal might be eliminated as well. So far I've shown you how in digital holography we can isolate one of the terms, the complex wavefront of the sample O, containing both the amplitude and phase profiles of the sample. But as soon as we have this element, we need to know how can we propagate into different axial locations inside the recorded 3D image. So if this is done optically, all we need to do is using a coherent wave in order to illuminate this film, and then I'm getting this 3D image floating in the air, as I've shown you in the second part talking about optical holography. But if I'm doing that digitally, I can actually simulate this project using Fresnel propagation. I'm taking this complex matrix representing the complex object wavefront, and I'm digitally convolving it with quadratic phase function, where in the argument here I have over z, and z is different axial locations inside the 3D scene. So each time I'm convolving it with a different quadratic phase function and changing the z, and then I can propagate inside the 3D scene. But this slicing is not perfect. In a certain slice I can still see out of focus light from other slice, but if these 2 slices are far enough from each other, I will still get sectioning or slicing between these several or 2 slices. Let's go back to a comparison between regular photography and holography. In this type of example, this is an on-axis Fresnel holography. So in regular photography, in classic imaging, as you can see here in the upper figure, what happens is that 2 points which are located in different axial distances project onto the image sensor different images. So the point which is in focus present or projects a focus spot, whereas the point which is out of focus creates a haze. Or sometimes it is even not seen if it is very far from the focus. In a holographic system, what happens is that each point projects a Fresnel zone plate. This Fresnel zone plate is actually a DC plus cosine of quadratic phase, x squared plus y squared over z. So this Fresnel zone plate, which might look like these circles, changes its frequency dependent on the point axial location. So even if the point is far from the focus, I will get a Fresnel zone plate with a different frequency. And this hologram is actually a superposition between the Fresnel zone plates of these 2 points. So a hologram of many points is actually composed of a superposition of these points' Fresnel zone plates. And when I reconstruct the hologram, I'm getting each time the focused image, but also see the out of focus objects. So the sectioning or the slicing is not perfect. As you can see in these examples in which I have several planes, the first cube, the second cube, the third cube, and the background, each time when I'm changing the reconstruction z, the z that I'm using in the quadratic phase function, when I'm convolving it with the hologram, each time a different cube or a different plane is in focus, but I still see the out of focus images as well.